Good morning, everyone. It is really a pleasure to host Professor V. Jagadeesh Kumar, Department of Electrical Engineering, IIT Madras, who kindly, accepted our invitation to come and share his thoughts on pulse-oximetry. Of course, as Dean of academic courses in IIT Madras, he is a very, very busy person, but in spite of his busy schedule, he could accommodate this lecture. So just to give a brief introduction, Professor Jagadeesh Kumar got his BE in 1978 from College of Engineering, Guindy, followed by MTech and PhD from IIT Madras. He got his PhD in 1986. He's a professor in Department of Electrical Engineering since 2000 at IIT Madras, and is presently heading the Central Electronics Center, as well as I mentioned, Dean of Academic Courses at IIT Madras. Received the Young Scientist Award from Department of Science and Technology in 1988 and DART Fellowship in 1997. He's guided 10 PhD scholars, 11 MS research scholars, and published 60 journals, mostly in IEEE journals, actually the top-rate journals there, and presented 120 papers in international conferences. He has 6 patents to his credit, and he's traveled widely across the globe. He spent a considerable amount of time at the King's College in London, Asian Institute of Technology in Bangkok, University of Braunschweig, and University of Aachen in Germany. And his interests are in measurement, sensors, instrumentation, and biomedical engineering. And that's the formal part, but I also want to mention that he's a teacher par excellence, and I still very fondly remember a lecture that I sat in a few years ago on RLC circuits. The concept that he taught and the lecture itself is still very fresh in my mind. So he's an excellent teacher, and we are really glad to have you here, sir. So look forward to your talk. Over to you.
Okay, thank you, Professor Balaji. I'm going to talk about a lot of work that has been done. You can see from the title itself in the past 25 years. The Odyssey started in 1995, and I'm grateful to all my students who worked with me in this Odyssey. Starting from Ramananda Rao, Reswana, Ashoka Reddy, Leo Mariappan, Bobby George. Bobby George is currently a professor in our group. Madhu Mohan, Gaurav, and Albina, and of course, few more students who are working now. Now, if you look at medical diagnostics, the moment you become sick, of course, you go to the doctor, he takes your temperature, he takes your pulse rate, looks for the breathing rhythm sound with the stethoscope, and if you are above 40, of course, he will also take your blood pressure and makes the diagnostics. And if that doesn't help him, he will give you further analysis. He may send you to a lab to take your blood sample and look for whatever pathogens he's looking at, or he will ask you to take an X-ray, ultrasound, endoscope, MRI, CAT scan. Of course, now today, it's really, really endless set of tests, right? Including the virus that we are now suffering from. Even though we are not having the virus, we are still suffering from the effects of it on the society. So if you look at blood analysis, the first part, that is, you look at what are all the constituents of a blood, right? Whether you have enough amount of hemoglobin, whether you have iron deficiency, all those things, right? Whether your eosinophil is at the right level. These are all one type of test. The other one is the dynamics of blood flow itself, right? That is another part of test that many are not really very familiar with. So I'm going to talk about the second part. This is the standard test that you do on blood. The second part is the dynamics. When blood flows through the artery, of course, you have huge pressure. I don't know how many of you have really looked at what is 120 millimeter of mercury pressure, right? It's quite high. In fact, the very first way they measured pressure was puncture an artery and put a capillary, and they kept on increasing the capillary height, and the pressure stabilized at about 3 meters. I have published a book where this photograph is there, the whole photograph. Maybe if you're interested, you can look at it. The second is the venous blood flow. Blood in the veins, when it comes to from the capillaries, is very low pressure. It's only about 15 millimeter of mercury, and obviously it is not enough to move the blood. So the movement of the blood in the veins is aided by the muscle pump, as well as the microvalves in the vein. Because when I have blood in my veins in my leg, as I'm sitting now, that has to come back to the heart. How does it come back to the heart? Because the muscle contracts and squeezes the veins, and there are a large number of microvalves in the vein that permit only the venal blood flow in one direction, that is towards the heart. As anything can go wrong, these microvalves also can go wrong, or the veins become stiff as you age. And if there is a problem with this, then you have two conditions. One is called varicose veins. The other one is called venous thrombosis. Varicose veins is is with anybody who is above 60 years old to various degrees. But venous thrombosis is a life-threatening. If you get it, you should be very, very careful that you remove it as soon as possible. So how do you test that you don't have this problem, right? There are two standard tests. So the tests are called venous muscle pump test, supine and vertical. The supine venous muscle pump test is very old and it's no longer used. The one that is current is NPT, which is the venous muscle pump test. So let me look at in the supine venous muscle pump test. You just attach a pressure sensor to your knee, near the knee. Ask the student to ask the patient to lie on a board and measure the pressure. Ask the patient to lift the leg. Obviously, the moment the patient lifts the leg, due to gravity, the venous blood will flow out. So you will get a pressure drop. Again, you ask the patient to keep the leg horizontal, and you take the time required for the pressure to come back. Of course, this, as I said, this is no longer used. Let's not discuss this. Mainly because it doesn't provide many parameters the other test gives. The other test, of course, pioneered by my colleague, my friend at the University of Aachen, Professor Vladimir Blasek, who is the father of this technology. So here you make the patient sit on a chair, put the sensor just below the knee, and ask the patient to perform the dorsal flexions. That is, you lift your foot and tap, right, 8 to 10 times. So if you do that, the muscle pumps will get activated and the blood volume in your leg will go down. And you ask the patient after he has done, ask the patient to stop. Once the patient stops, the blood volume will again increase. Blood will flow from the capillaries and reach. So you find out this amplitude and the time taken for the venous to refill. So we call it as venous refilling time, VRT. And this is V0 is called the muscle power, muscle pump power. And these two give the physicians whether the the patient is all right in terms of varicose veins or venous thrombosis problems. So now the sensor here, traditionally it was a pressure sensor, and then Professor Blaszek started working on optical sensors and used just light to get the signals. So if I put a light on the skin, the light goes in and comes out. Of course, most of this light comes out. That is why our color of the skin we see. But quite a few millimeter inside, the light penetrates and comes out. So if I look at the light that comes out, it reflects from tissue, venous blood, as well as arterial blood. So in terms of the absorptions or reflectance of light from our body, especially on the top layer near skin, of course, this is the wavelength dependence on epidermis, and this is bloodless skin, about 60%. And if you look at this blood layer, about 120 micron inside, right? And very little light comes out of the blood. If there is blood layer within this window, very little. What does it mean? So this was the first experiment I conducted way back in 1996. We actually, this is my right hand. I had to put the right hand mainly because the microscope, the IR microscope, the adjustment was on the left. I don't know why they did that. The photograph that you see is actually about 4 or 5 millimeters of my right hand top. And you see that if I take it at the IR, I see only blood vessels as dark lines against a white background. Right? This is no gimmicks done, just the IR photograph of my hand. What does it mean? Which means if I now look at the infrared light that is coming out, right, and the attenuation of that light is only due to blood vessels. So any measurement I do on this light, there is a big contrast. Nothing else really contributes, only blood vessels contributes. So we can now make a sensor. This is the optical sensor. Before I started this lecture, I was talking to Professor Balaji. I told him in terms of optical sensor, the sensor that I use is really nothing. It's just a photodiode. So I have a small sensor where I send infrared light into the skin and detect. And we use a photodiode mainly because the phototransistor and light-dependent resistor, they have nonlinear characteristics. Photodiode has a very linear characteristics with respect to intensity. That's it, right? So if I detect this signal, what will be the components in the signal? There will be large amount of light that comes from the epidermis, dermis. Then a small amount comes from the slow-moving blood in the capillaries, and slightly higher frequency from venous blood. And of course, arterial blood will be pulsating with respect to the heartbeat, right? So you can detect all this. I'll show you the actual signals later. So what can we do? With the single wavelength, only with IR, you can detect varicose veins. And with IR, as well as with the tourniquet, you can detect venous thrombosis. You can also measure arterial pulsation and pressure. When I say arterial pressure, you cannot measure systolic and diastolic. You can measure only an average pressure. With two wavelengths, we have already worked on it, arterial oxygen saturation and hemoglobin concentration. Both my group has worked. I'll explain how this is done. And in principle, with 3 wavelengths or more than 3 wavelengths, you can measure blood glucose level. This is a very big challenge. At least 15, 20 groups all over the world are working to crack this. It's a very difficult problem. So if somebody cracks this, they'll become a billionaire. Because right now, the only way you can measure blood glucose is to draw blood, either a drop of blood on a very inaccurate blood glucose meter or a 1 cc of blood for titration using sodium lauryl sulfate method. So this, we already said how to measure venous refilling time. We simply put a PPG sensor, right? And measure the changes in the reflected light. But it's not that easy, right? Why? Because if I look at the detected light, the detected light is emitted light intensity attenuated by the epidermis absorption or reflectance, and then the coefficient of absorption. Then it's a function of tissue, venous blood, arterial blood. But what is the problem? The problem is these two parameters depend on patient. If I have a white skin patient, why does the skin look white? Because most of the light is reflected back. That's why we see the patient skin as white. If I look at an African origin person, his skin really looks black, right? That's because most of the light is absorbed by his skin, right? So if I look at a particular volume of blood here and look at the reflected light, if I have white skin, I get a large reflection. If I have a very dark skin, the black person, I get small one. And of course, this is somewhere in between. So I can't make any measurements because of this particular problem. But whenever there's a problem, there's a solution. So the first solution, this was actually done by Professor Blaszek. So that's why I have given the reference here. We looked at this. The detected light, oh, this must be I suffix D, sorry, is emitted light into all this. Now, if I look at this portion is DC. If I make this portion constant for all the patients, what does it mean if I make the constant? I adjust IE so that this portion, IE into 1 minus KCR into KCA, become constant. Then the detected light, I can put it as K into 1 plus the function of tissue, venous, and artery. Now you remember this K is a constant, so I can now make measurements, right? Differentiate between patients with, right? So how do I make that a constant? I take the PPG sensor, take the low pass filter, I get only DC. I compare the DC with the reference voltage. If the reference voltage is more than the PPG DC voltage, I decrease the LED driving current. And if it is not, I less. So this continuously adjusts so that the DC value of the detected diode output voltage is constant, right? For all patients. So which means I've removed the patient dependent parameters, I can make measurements, right? So at this point, of course, I started collaborating with Professor Blaszek. This was the first work done by Leo Mariappan. Is it possible to model this process, right? I have the light that goes in and comes out, right? And of course, it doesn't happen like this, like a this thing. It's just scatters around, right, and comes out. Okay. So the thing is, if you put scattering, modeling becomes very difficult. So from the detector, if I look at it, we made that it to be just like this. Now, if I put the source and the detector on one source on one side, detector on the same side, this is the cylinder that comes out. So this is the V-shaped cylinder now made horizontal, and I have input light at a particular wavelength, and I have the output that is going to the detector. Now, how do I look at it? I take a small disk in this path of light. I again repeat, this is not a cylindrical path. It's only an approximation. but you will see that the approximation holds good. So the disk has an area A. It has all the cells depending upon where the disk is. If the disk is here, it will be only epidermis cells. If the disk is somewhere here, it will be only dermis or skin cells. And if it's slightly inside, it will be tissue, venous blood, and arterial blood, and so on. Right? So I take the thickness of the disk as DL, and input intensity is IL, and the attenuation as DIL. This is for making a model. Right? So, for example, I take one cell, let's say tissue cell. Right? Those of you who are non-vegetarian will immediately understand the tissue looks brown, so that's why I colored the cell as brown. So I have some input intensity Ix, I get some output intensity Ik, some gets absorbed, some gets reflected or scattered. Right? Now I have to find out the attenuation due to the blood. Believe me, we tried to model this. It is really, really very complex and not possible to model. One day when I was discussing with Leo, I told him, Leo, we are not interested in all the things that are going on in the optical world. I want to model what is input and what is output. Right? So I have 100 candela I am giving here. I am getting, let's say, 80 candela, which means I can put this tissue as 80% opaque, 20% opaque, and 80% transparent. So if I give 100 candela, I will get 80 candela. Of course, this is wavelength dependent. At a particular wavelength, whatever is the attenuation, I don't have to really worry about what is scattered and what is transmitted, what is absorbed. I make this top-down approach. Right? This binary equivalence of the absorption of the cell is really nice because you can now model everything. Right? Okay. I can now say the opaque area is this sigma tissue lambda into number of cells in the disk. What is the number of cells? The concentration of the cell in that area, the area of the disk, and DL. Right? A into DL is volume of the disk, and A is the cross-sectional area, sigma is the equivalent opaque area, and cell concentration. Right? Okay, now we come back. I know how to model this. Now I'll have to take the total opaque area in the disk. So I can now add all the parameters. The total opaque area in the disk is, if epidermis is present, is concentration and the volume of the disk. If dermis is present, its concentration and volume of disk. So like that I can put. And if you see, all these, I have not put any this thing. Here I put subscript T, because blood varies as time varies. Blood flows, there's a dynamic property. So that's why this is only the only parameter that varies with respect to the time in the window of measurement. Of course, epidermis, dermis, tissue varies, but varies over a day or a week or a month, not in the small few seconds I measure. Right? So here again, these are the opaque areas and these are the concentrations. Okay. So if I do that, now I come to the analytical model. The attenuation across the disk is the input intensity I into total opaque area by total area. Right? That's very clear. And why did I put a minus sign? Because attenuation, it is reducing. Right? So di by dt would be negative. Okay. Now I can write this equation for di and bring the I on this side and integrate this disk from 0 to full. What is 0 to full? 0 is at the source, L is at the detector. So if I keep moving the disk step by step through from the source to the detector, I get the complete attenuation. So if I do this mathematically, I get the equation as ln I lambda by lambda into all this. Don't be intimidated by all these numbers. We will see later many of these things we'll throw out. We don't need them. What we need is only blood, right? The rest we don't want, right? So if I now take ln inverse and take the I lambda on the other side, I get I naught lambda. This is the detected light on the photodiode, right? Which is my photoplethysmogram, is input intensity of light into e power minus all this. This looks exactly like the Beer-Lambert's law for attenuation of light in a solution, right? Uh, it's nature, so everything works the same. Now, if I now put a diode and detect this light, the output from the diode or diode detector circuit V naught lambda will be sensitivity of the diode into the intensity of the diode, that is intensity of the light that falls on the diode. So I simply multiply this. Now, if I take the logarithm at the output of the detector, that is, this is the output from the photodiode, I take ln, I get this equation. Now, what I do is I take ln V naught lambda t equal to 0 and subtract it from the future ln V naught lambda. So I take a signal which is S lambda is ln V naught lambda minus ln V naught lambda t equal to 0. When I say t equal to 0, at whatever point I am doing the experiment, right? And I see that I get only this, right? The moment I looked at this, the first thing that came to my mind, I told Leo, this is wrong. I don't accept. All the work that you have done has gone to dogs. Right? So, can anyone tell me why I said this? Because this is my output signal, S lambda, but where is my input intensity? I lambda, it's not there. Where is my diode sensitivity KD lambda? It is not there. So it looks like I am getting a signal which is independent of my instrumentation. I can have a diode giving 1000 candela or 10,000 candela, I will get the signal. I can have a detector with a gain of 10, 100,000, 100,000, I will still get the signal, right? So it becomes independent of input and instrumentation, which is not really right, right? So I, myself and Leo, we sat together, we went backwards, forwards, to find out whether we are making a mistake somewhere in the derivation. Then after 3 months, I said, I mean, whether we are doing something really stupid or this is really right, right? In fact, Leo quipped, sir, if you look at the Sherlock Holmes novels, Sherlock Holmes always says, if you remove all the impossibilities, whatever remains, however impossible, must be the truth. So he said, maybe it is correct. Then I said, okay, we will test it. How do you test it? You make an experiment. So this is a sensor which has a diode and a photodetector. And this is a photodetector signal conditioning circuit. So one current to photocurrent to voltage amplifier and another amplifier. And we put a data acquisition system. And what we did was we varied the intensity of the diode by changing the current. If I put the switch here, I will get a full Zener diode voltage here. And the current here, ID, will be Zener diode voltage divided by RT. If I put a switch here, it will be part of the Zener diode voltage. So this VD decreases, this VD decreases, ID again will be VD by RD decreases, right? So 3 possible currents. And we made an experiment, right? So this is the result of the experiment. Of course, if I take the actual signal that is coming from the photodiode, when I have 4 milliamperes, I see that the signal is low. If I have 6 milliamperes, a slightly higher amplitude, and this is the highest amplitude. Now, from these 3, if I calculate S lambda as ln of V lambda minus ln of V lambda at t equals 0, I see that all are the same, which means they are giving me only the blood variation in the sensor, right? The sensor output, which is responsible for from the blood alone is. So now I can do all sorts of measurements on the blood, right? On the blood flow, because I have a signal which is only proportional to blood flow. The skin color of the patient is immaterial. Even the instrumentation is immaterial. I can give a gain of 100. I can give a gain of 50. I can have a diode which gives me 100 candela. I can have a diode which gives me 300 candela. Doesn't matter. I will get my signal, which is only proportional to blood. So we went ahead and tested. Again, if you see, this is the gain of the instrumentation amplifier. And we saw that the measurement on the blood is exactly the same, even if I increase the gain by 10 times, 5 times, right? This is the gain of the second amplifier in the circuit. So obviously, what do? You publish your work. We also took a patent. I'll talk about the patent a little later. And the first paper was IEEE I2MTC in Singapore, 2009. And the second paper was another paper by another set of students who built an instrument in another I2MTC. Now we already...
excuse me, sir. Shall we take a few questions? There have been some questions in the chat box.
Okay. Can you read, because my screen, yes, I cannot...
I will read it out. I just wanted to let you know that I'm interrupting.
Okay, no problem.
So the first question is about the venous flow measurements that you mentioned early on, where somebody is like tapping their foot and then you have... so what are the typical time scales involved? What sort of bandwidth do you need to capture those sort of signals?
No, these are very slow varying. You tap at the rate of about 1 every 2 seconds or so. I can actually tap and show the...
Okay. So
like that, right? So you just lift your foot, tap again, right?
Okay.
And you have to do 8 to 10. It really doesn't matter. As long as it is greater than 8, it is immaterial how many times you tap. It reaches a saturation.
Right.
Then you stop. It takes about, if you are a healthy person, the venous refilling time is roughly about 50 seconds.
Oh, okay.
Greater than 50 seconds.
Okay.
And if you have a problem, then it will be less than 30 seconds. If your VRT is less than 30 seconds, you have a problem.
Right.
So 30 to 60 is gray area. The doctor has to do something else to test you.
Okay.
Next question.
I suppose we've not discussed noise so much, but in terms of mitigation of noise, I suppose you would use a low pass filter or maybe do some runtime averaging to make sure your signal to noise ratio is good.
Yeah, the basic thing is for the venous refilling time, noise is a problem, not a problem. Because the signal that you get is very high.
Right. Okay.
Hundreds of millivolts from the diode itself. Right. So when we go to the pulse oximetry, that's where the noise comes in. We'll have to do a lot of filtering. Here we did not use any filter.
Okay, no problem. So the other question is, you talked about 2 different configurations. One was actually reflecting or a scattering configuration. The other one was actually a transmission type configuration, like what the model that you mentioned was more like a transmission.
No. I'll go back to that. And this is the one.
Right.
So if you look at it, I have to model input output.
Right.
Some light is given and some light is coming out.
Okay.
Right. But what actually happens is some light gets absorbed, some gets scattered, some goes through. Okay. And if I have to take all these characteristics into account and make a model, it is very complex. We tried all sorts of modeling techniques. including the Monte Carlo method. But you don't get anywhere. It's so complex, right? But on the other hand, if I really look at it, what I am interested in, I am giving a light input, I am getting a light output.
Right.
I put a black box in between.
Yeah, yeah.
I just assume I am giving a light of 800 candela, I am getting 80 candela. 20 is eaten away by the black box.
Okay. Okay. So it doesn't matter whether it's a transmission configuration or
no, I don't care what happens inside.
Right. Right. Okay. So
it's a very top-down input-output model, and it works.
Right. Right. Okay.
So many times that's what I keep telling students. Simple things are the best things. Right?
Yes. Yes.
Of course, we analyze complex. This process is really complex. But the method that we used is only simple.
Right. So one more question, sir. You talked about adjusting the intensity for different colors of skin and so on.
Yeah.
So the question is, how do we generalize this equipment for any person?
No. That was the old method, which was pre-90.
Yeah.
And today, of course, we don't use that. We still use that to optimize the instrumentation. But the moment you use the model, as I told you, the nothing matters.
Yeah.
Right?
Yeah.
I can change the diode with a different sensitivity. My system will still work.
Yes. 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 And the related question is also about the arterial walls and the venous walls.
There is no valve in the artery.
No,
the pressure is so high. Only micro valves are there in the veins.
Okay. The wall has
I am really sorry. I am not on a one-to-one in the class. Otherwise, I suffer from varicose veins. I could have shown them my foot. Right? I showed them the bulging of my veins. In fact, I cannot stand in a place for more than 3 minutes. I'll faint.
Right. Yes.
Right? Because I have to keep moving for my venous blood to go up.
Yeah. But in general, any extra absorption beyond whatever you're shown, they will all get cancelled anyway.
Yes.
Because of that reference measurement you're taking. It is very important. And that actually brings up the question. So you mentioned T equal to 0. So T equal to 0 should hopefully be a measurement where the blood absorption is relatively lower, right? So that you can actually zone in on the blood absorption component itself.
Yeah. The basic thing is at infrared, blood absorbs almost everything. So it looks like a black. Only 15% of the light that goes into blood comes out at infrared. So it looks like a black line against a white background.
So you would use basically one of those things,
Yes.
one of the points where there is very little absorption, and then use that to basically.
No, we can do this any part of the body. All over skin, behaves exactly the same. Whether it's my forehead or my forearm.
Yes.
Right?
Yes.
It behaves exactly the same.
Understood. And one last question. You gave us a teaser basically about this glucose measurement, and you talked about a third wavelength. Maybe you'll come back to it.
No, I have
a third wavelength. What is it?
No. I'm not going to talk about it. Okay. But it is possible. See, the thing is, glucose also has its absorption frequency.
Right.
So you put absorption frequency light, and there are problems. The light wavelength that is sensitive to glucose, it's not very nice to use those wavelengths. You may end up triggering a cancer, skin cancer on the patient. Right? So there's a lot of problems, but in theory, you can do that.
Okay.
There are practical difficulties. As I said, there is a very big group in Cambridge working on that. In fact, they invited me there to brainstorm with them, and we couldn't get out of the problems. As on today, it looks that we cannot solve problems.
Okay.
But there is, in my opinion, there is no problem which can be left unsolved.
Sure.
Right? We can crack it someday,
Yeah.
maybe.
So far you have talked about single wavelength only.
Single wavelength.
I think you will go on to maybe two wavelengths.
Yeah. Quickly.
Okay,
so
fine.
Single wavelength, we can do vein occlusion test. I'm not going to details in this because this has nothing to do with optical sensors. You can actually measure venous pressure. Then you can measure arterial pressure. Now we come to the oxygen saturation. With two wavelengths, we can measure oxygen saturation.
Okay.
What is oxygen saturation? The arterial blood contains hemoglobin with oxygen. Of course, for various reasons, this oxygen level can go low. For example, if you are ill, then the hemoglobin content itself gets reduced and your oxygen gets reduced. Or if you're ill, some of the hemoglobin may be killed. We call this as methemoglobin. And or if you absorb carbon monoxide, of course, again, carbon monoxide kills the hemoglobin from carrying oxygen. So we put the oxygen saturation as amount of hemoglobin in arterial blood that is carrying oxygen and amount of total hemoglobin. It's a percentage. So I don't know, because of this virus, this pulse oximetry has become very popular, right? How is it done? Again, you have just one LED, one photodiode. That's the photosensor, right? My entire work, I have used only one optical sensor, that is photodiode. So you send light and receive light. We have already seen this. We have already seen this equation. So what you do, this was again typical. You take the red wavelength, find out the pulse magnitude divided by the DC that comes out. Again, take infrared wavelength and plot this against pulse oxygen saturation. This is 1974 or 76, I'm not sure. This equation is actually from Japanese researcher. So most of the pulse oximeters that you buy today use this calibration, especially the cheap one. So you simply take this ratio of ratios and calculate the oxygen saturation. So here, what we did was, we again have this model. We now look at the blood and I'll skip this. This is not enough. So if I look at the infrared PPG peak value, I see that it is hemoglobin concentration and oxygenated hemoglobin concentration, right? Again, I take the infrared hemoglobin concentration, oxygen. I just divide the detected voltage at red wavelength, detected voltage at infrared wavelength, and I can easily calculate the oxygen saturation like this, right? The advantage of this method over the this particular method is that it is not empirical. It is it comes out of the patient itself, and these are all constants, right? Where R is the one that I measure. This R is the one, right? So we again tested this, and you calibrate everything. Okay. Oh, how much time we have? Okay, we are almost through.
Yeah, another 5-10 minutes is fine, sir.
Okay, right. So I'll simply go through it. So if you look at this, this equation says the red amplitude, right, is the extinction coefficient of hemoglobin at red, extinction coefficient of oxygenated hemoglobin at red, into the ratio of hemoglobin to oxygen and hemoglobin, concentration of hemoglobin, and of course the path length. The TF is the path length, right? So we thought if I do this, I can measure this concentration of hemoglobin, right? So to get concentration of hemoglobin, I should know what is TF in this equation. So we made measurements. We measured the finger thickness because you put the sensor on the finger, right? One side LED, one side photodiode. So the thickness we thought would give us this TF. But it doesn't happen. If you look at it, it's all over the place. This is with respect to peak to PJF and the thickness that we actually measured on patients, right? So then we went back. This is again the same equation. And so why not plot these equations as such and see whether I can get the TF. So we did that, plotted, sort of, we got a linear. Those of you who work in the curve fitting, you will know this is the straight line fitting for this data. And this is called regression analysis, R square. If it fits exactly, it must be 1, right? But I got 0.866, which is about 15% error, right? So not really good. You can't have a measurement method, especially in biomedical engineering, with 15% error. And this was done by Albina. So after about struggling for a week, I told Albina, segregate the data as male and female and do the same thing. So when she did that, we hit a jackpot. If you look at for the male and female segregation, it is 0.963. It should be 1, but it's very close to 1. 0.963 is only 4%. Here it's only 3%. So you use 2 sets of equations to measure for males and females. Then you actually get hemoglobin measurement. So this is actually what the patent that I sold, Balaji. So you can make hemoglobin measurement. Of course, we went and made the test, right? So this is the kind of error that you get compared to the present method. But to our horror, if you go to the laboratory and test it today, right, they use what is known as the SLS method, sodium lauryl sulfate method. That itself has an error of 15%, right? So ours is only 4% or 5%. It's much better. Okay. Now, the entire work, I have given you the set of publications. So the most recent is on the top and the oldest is the bottom, right? And you can see there are, one journal paper is missing. I will give you, Balaji, 3 journal papers and a large number of conference papers. And as I already said, Ashaka Reddy has done his PhD, Madhumohan, and Nirupa did her MS.
Great.
So the thing is, have an idea, right? I mean, it started in 1995 with just one photodiode and one LED, right? And that has really potential. All you have to do is think how I can refine. Think how I can get a better method. I can solve problems that is in the existing method, right? Keep on doing that. You would definitely go. Okay, I know the second part I have rushed through, but basically there is really not a big deal. Once you have understood the venous refilling time, it is exactly the same, but for 2 wavelengths. That's all.
Yes. First of all, I thank you for this nice presentation that you have. There are still a few more questions, yes, so I will actually read it out.
Yeah, read the question, sir. I'm only seeing my screen. I'm not able to see anything else.
Sure, no problem. So the question is about what is the normal frequency of operation for the pulse oximeter?
Okay. Actually, our heart rate is anywhere between slightly less than 1 hertz. Athletes will have something like 0.8 hertz, 45 beats per minute. And normal young people will have 60 beats per minute.
Right.
So one hertz frequency. And old people will have about double, 120 hertz.
Right, right.
But
okay.
the thing is, it's not a sine wave. It has a kink. You see, that's a dichrotic notch.
Right.
That comes because of the pulsated flow of blood in the arteries. There's a reflection, right? And if you want to do that, you need to go up to about 20th harmonics. So typically 20 hertz is good enough.
Okay.
But what we do is we go up to 40 hertz.
Okay, okay.
So most of my instrumentation, the bandwidth is kept at 40 hertz.
Of course, when we do at low frequencies, the 1/f noise is a problem, right, sir? So how do you deal with that in your case?
No, in the method, if you see, I have a photo detector output. I immediately apply logarithm. The moment I apply logarithm, I hope I am in a class. I can go to the board and show you with synthetic examples.
Right.
The moment I apply natural logarithm on my signal, the noise gets attenuated like anything. Right? Because if you take a random signal and apply e power x, e power minus x, then it simply vanishes out. Right? And there is a secondary benefit. If you look at all my signals, the DC is 90%. Right? Because most of the signal comes from my skin or my tissue or my bones. If I put it across the finger, there's a soft bone inside.
Right.
Right? 90% of the signal is DC. So that gets really attenuated to a very small amount. And my contrast between what I am interested, which is the pulsating signal, and what I am not interested, which is DC, enhanced by e power inverse. So now my signal becomes, instead of 1090, becomes 9010.
Right, right, right.
So noise was not at all a problem in PP.
Okay, okay. So of course, when we talk about general instrumentation, if we really want to push it to the limits, you could possibly use lock-in detection as people explored that option of going out to basically modulating your source and at a higher frequency and then locking to that, and then that can really take you to the, although as you mentioned, noise may not be as much of a problem, but if you really want to keep it down, you could potentially go to that extreme.
No, I have not seen a single work on using that, mainly because in the normal instrumentation itself, you get really very good signal.
Right, right, okay.
I mean, the output from the photodiode would be tens of millivolts, not millivolt. So it will be above the noise floor of the instrumentation, and you don't have any problem.
Okay, 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 good. The two techniques that you mentioned, sir, for pulse oximetry, actually, that is a personal question from my side. Actually, I didn't quite appreciate the difference between them. Both of them use two wavelengths, right?
Both of them use two wavelengths. One uses an empirical equation.
Oh, okay,
One
okay.
uses the actual equation through modeling.
Okay, okay. And
the second one is a little more complicated to compute. Right? So you will see that only in expensive instruments.
Right. And calibration is a big issue in a lot of these instruments, right?
No, so, because you make ratiometric measurement.
Okay.
And your empirical equation is automatically calibrated.
So when you talk about SpO2 versus that ratio, that curve was, I suppose, the first method, there was an empirical, what you're mentioning.
Yeah. See what happened was initially when the Japanese made the first instrument available,
Mm-hmm.
because their instrument was not as cute as the one that we use today. There are several other groups, especially Philips Eindhoven, Hewlett Packard. Hewlett Packard had a long presence. Nelcar.
Right.
All these made their own testing.
Yeah.
So, in fact, what they do is they take volunteers, ask them to take a reduced amount of oxygen. So they actually lower their blood oxygen.
Oh.
And take the red and infrared PPG measurements. And there is a gold standard. I forgot to tell you the gold standard. Gold standard is called the blood gas analyzer, VGA, which actually tells how much of oxygen is there, how much of carbon dioxide is there.
Oh.
But to do that, you have to puncture an artery, take about 3 cc of blood.
Okay.
Which is very dangerous.
Yeah.
Right. So the initial calibration, getting that equation 110 minus 25R, as well as my equation, we had to do those tests.
Okay. So that's nice.
So that's clinical validation that is done only by the certified laboratory.
Yeah. So what is an acceptable error in the oxygen saturation? I suppose you are working in a very small range, right? I mean, if it's less than 90, it almost
one good thing about Balaji, one good thing about our physiology is that there is nothing like precisely. See, earlier they used to say 110 milligram of per deciliter of glucose is necessary. Right? Now they say no, up to 90 is also okay. Right? Similarly, oxygen saturation. Earlier there was a very big debate saying that you should have 95 and above.
Yeah, that's what I heard. Yeah.
And then when they went and measured people in Himalayas, they are all surviving with 85.
Oh, okay.
Right? Your body gets adapted.
The body adapts.
And I mean, they are much better than us.
Right.
In terms of in that atmosphere.
But
in fact,
the measurement scale is actually the useful scale that you design the instrument for is only the 20-25%.
Yes, 80 to 100%. Because if it is less than 80, you will you see your brain needs. Again, this is another information. Our body is really complex, and sometimes you don't realize. My brain weighs only 1 kilogram. But it takes 60% of the oxygen I generate through my lungs. Only 40% goes to the other parts of the 84 kg of my.
Right.
So brain needs a lot of oxygen.
Yeah.
And if the oxygen level reduces below 80%,
right,
you will faint. No one in the world so far today has survived at 80%.
Yeah.
So you will be in an ICU if you are let.
Right. Of course, we do hear about those cases more often these days than normal. And
so more than percentage, the actual thing is it's anywhere between 9 milligram per deciliter to 13 milligram per deciliter. If the amount of oxygen is less than 9 milligram per deciliter in your blood, your brain will shut down. There is a mechanism. It's not that you will die. Your brain will shut down. And you can revive if you do very quickly. Otherwise, you will go into coma.
Right. Last question from my side, and then I'll look for some other questions if there are from the students. The ADCs that you use for these applications, what is the level of precision that's required there? How many bits?
Initially, I used 12-bit. Then graduated to 16-bit.
Oh.
And today, I use 23-bit.
Wow, really?
Because the frequency is low. You can get a 23-bit ADC.
But are you using the 23 bits? Because from what you mentioned that with the noise being so low that...
No. I can show you the data. I'll send you the data. 23-bit ADC, each bit counts. What I do is I remove all the unwanted noise at the beginning itself by applying logarithm. So I don't have noise in the digital output.
Okay. But
The advantage of a 23-bit, I mean, you really don't need 23-bit. 16-bit is more than adequate, much more than adequate. 12-bit itself is good, right? But 23-bit, we simply use because today you get a 23-bit 2 kilo samples per second. You see, you don't need
that's
large
right.
samples per second.
That's right.
23-bit 2 kilo samples per second is only 300 rupees.
Yeah. So why not?
So why not use it?
That's
Whereas 16-bit, whether you go to analog devices or Texas Instruments, is still about 4,000, 4,500. So thanks to all these cheap pulse oximeters,
yeah.
The 2 kilo samples per second ADC 23-bit has really dropped down in price.
I didn't know it was so cheap actually. Yeah.
It's very cheap.
Thanks for that information. I am just pausing to see if there are any questions, guys. If you have a question, you can ask now. Otherwise, of course, we can ask Prof. VJK separately offline as well. So with that, let me close the session, sir. Thank you very much once again for sharing your wide, deep experience in medical instrumentation.
Of course, this is an optical sensors course, but you can see with a very simple photodiode, you can do so much.
Right.
You will see that the optical sensors have really a very large application potential.
Great. Thank you, sir. Right. Thanks for your time today.
See you all.